lecture introduces autonomous equations, a special kind of differential equations. So autonomous equations are the equations that the derivative of the dependent variable dy dt is not explicit on the independent variable t. Yeah. By the definitions, an autonomous first order equations is one of the equations that has a following form. Again, the derivative of the dependent variable is equals to a function in terms of the dependent variable y. Again, it's not explicitly depends on the independent variable t because you don't have any t on this side. So here's some example of autonomous equations, first order, dy dt equals to, let's say, 2y minus 1, okay? And this function 2y minus 1 here is a function f of y. It's a function in terms of y and it's describing the derivative of y. Another example can be dy dt equals to sine of y times y squared minus 1. Again, this is a function f of y, and you don't have any explicit functions of the independent variable t in these functions here. So these two here are the examples of some examples of autonomous first order equation. Why? And the question is, why should we care about these types of problems or these types of equations? Well, it turns out that we can analyze the solutions of these equations without even solving them, right? For example, if I don't know how to solve these two equations, but because they are autonomous equations, I can try to analyze the ending behavior of the solutions of these two equations. Well, let's look at the general equation, a generic autonomous equations when f of t is a line ay plus b, where a and b are constants and a is positive and b is negative. So if we look at this differential equation, y prime equals to a times y plus b, the first thing we notice is, again, this is an autonomous equations. Okay, and since it's autonomous equation, we have f of y equals to a y plus b, y prime equals f of y. And then from here, we can find equilibrium solutions, where what are the solutions of y, so then y prime equals to 0. F of y equals to 0. When f of y equals to 0, that means ay plus b equals to 0. That means y equals to negative b over a. Okay, and since we said that b is less than 0, a is greater than 0, then negative b over a will be positive. And if you look at this f of y functions by itself, right? So this is a line, it's a linear equation. And if I want to draw a graph that describing y and y prime, so I have y as the x-axis and y prime as the y-axis, then the relation between y prime and y is described using this linear equation here. And then we know that negative y b over a is positive, then y equals to y prime equals to 0 when y equals to negative b over 8. That means if b is here, then negative b is a is here, then this is the line that's go through this y. This is the line ay plus b right here. Okay, so if we look at this line, this graph, describing the relation between y and y prime using this line ay plus b. You notice that if I pick a point on the left side of negative b over 8, then my y prime will be negative. Okay. So let's make some observations. If a y0, okay, a point y0 less than negative b over a, then the derivative y prime will be is the same as f of y. Okay. Then if y0, just pick a point y0, and if the point y0 here is greater than negative b over a, then the y prime or the f of y will be positive. So when y prime is negative, what does it mean? That means the solutions of this equation here is decreasing, because y prime is the derivative of y, and if y prime is negative, then the solution is decreasing. Similarly, if the y prime is positive, then the solution y of t is going to be increasing. All right, so that's some observations that we could make from the functions f of y equals to ay plus b. And since y prime equals to f of y, then we can make some conclusions about the derivative of the dependent variable depending on the point of y. So again, if you pick a point y, right, and it's less than negative b over a, then the solution curve y of t will be a decreasing function. And if pick a point y greater than negative b over a, then the solution curve y of t will be an increasing function. Next, let's look at different generic equations when f of y equals to a times y squared plus by plus c. And again, this is a parabola, right? It's just the second order of linear equation. And more specifically, a will be positive and c will be negative. So again, if you have y prime equals to a parabola, equals to a quadratic, then you can easily find equilibrium solutions, is the solutions from which the derivative of y equals to 0. So if you set y prime equals to 0, that means ay squared plus by plus c equals to 0. Okay, and since this is a quadratic, we know how to solve for y. And since we know that a is positive and c is negative, then a times c here will be positive. If a times c is positive, is negative, if a times c will be negative. If a times c is negative, then negative for a times c will be positive. That means this functions here, this equation here, has two real solutions, right? So then you have y1 equals to negative b minus b squared minus 4ac divided by 2a, and y2 equals to negative b plus b squared minus 4ac divided by 2a. So since this is the parabola, we can try to graph a graph that describing the relation between y and y prime. A is positive. That means this is an upward parabola, and you have two real values. So I imagine I said this is y1, a smaller value, and y2 is bigger value. And then this is an upward parabola, so this parabola will probably look like this. Okay. So this is the graph that illustrating the relation between y, the dependent variable, and y prime, the derivative of the dependent variable. So let's make some observation here. First, if I pick a y0, right, a point y that is less than y1, or y0 is greater than y1, then y prime here will be positive. y0 is greater than y2. Again, if y0 is less than y1, or y0 is greater than y2, then y prime is positive. If my y0 is in between y1 and y2, then the derivative y prime will be negative. Okay. And again, and then what is y prime? In this situation, by the definitions, y prime is the same as f of y 0. And this is equivalent to f of y 0. Because y prime equals to f of y. And if you plug y0 there, and then plug 0 into the function, then you have f of y0. Okay. So from these observations between the relation between y and y prime is actually just the function f of y. How can we describe the behavior of the solution? The solution curve y of t of a DE of an autonomous equation with an initial value y0 here. Okay. So in this case number 1, if y of 0 is positive, then what does it mean? That means the y of t will be an increasing function. F of y0 is the same of y prime when y equals to y0, right? And it is positive. That means the functions y of t will be an increasing functions. Make sense? In the case that f of y0 less than 0, and then what does it mean? That means that the functions f of t will be a decreasing functions. And it's less than 0. That means y of t is a decreasing function. What about when f of y equals to 0? F of y equal to 0, then the derivative equal to 0. If the derivative equals to 0, that means y of t is a constant function equals 0, y of 0 as a constant function. That means the function is not changing. It just keep, if you're starting at the point y of 0 when f of y equals to 0, then the functions y of t will stay the same over the time. All right, so we just make some observations using two is has the f of y is as a linear equation, and the second equation has the f of y as the quadratic equations. And so we can see that in both of these examples here, we both want to find the equilibrium solutions where f of y equal to 0. Okay. So once we determine f of y equals to 0, we can make some observations about the value of y compare with these equilibrium solutions here. So if you pick an initial on the right side of this equilibrium solutions, then the derivative of the solutions will change from negative to positive. And since the derivative changed from negative to positive, then the solution curve y of t will change from decreasing to increasing here. In a very similar fashion. If you have a quadratic as a f of y, again, you just need to find equilibrium solution when you set the function here equal to 0. And then since you have a quadratic, then you have two different equilibrium solutions, y1 and y2. And then you have 3 intervals to make comparisons for your solution curves, right? So for example, you have y1 and y2 as equilibrium solutions of this equation. Then if y0, which is the initial point, a point where you started, if y0 is less than y1 or greater than y2 on this side, then the y prime is positive. If the y prime is positive, then the solution curve should be an increasing function. Versus if y0 is in between y1 and y2, then in this case, the y prime will be negative. And if y prime is negative, then the solution curve should be a decreasing function. And if you start at one of the equilibrium solutions, then your functions, the solution curve y of t will be always equals to the starting point y0. If y0 is 0, whereas f of y0 equals to 0. Now, how can we analyze solution curves in initial value problem, especially in autonomous equations? First, we want to draw a phase line. So what is a phase line? A phase line is a visual description of solution trends as t goes to infinity for the solutions of autonomous equations. Okay, so phase line is a vertical line. So first you draw a vertical line representing the y-axis. Okay, so on these vertical lines, you will plot critical values, or the value at which f of y here equals to 0. I have two critical values, y1 and y2. And that is, I want to identify the trend of the function f, right? Is f of y is positive, f of y is negative, using the upward arrow and the downward arrow. So if the functions f of y, when y is greater than 1, this is positive, this is negative infinity. So if f of y here is positive, then you have this upward arrow. Okay, and then if f of y here is negative, then you have this arrow. And then f of y here is positive again, then you have this upward arrow. again